That faint, red spark in the night sky has captivated us for as long as we have had eyes to see and minds to wonder. For generations, our stories filled its alien landscapes with bustling cities and dying civilizations, grand canals stretching across deserts of red sand. But what if the first true hint of life on Mars was not a ruined citadel or an alien fossil, but a subtle chemical stain on an arrowhead-shaped rock? This is the story of that very possibility, a tale that pivots on a recent discovery made by a six-wheeled rover in the dust of a long-dead river delta. There, a peculiar stone nicknamed Chayava Falls, covered in leopard-like spots and poppy seed textures, presented a chemical riddle that could be the culmination of our centuries-long quest. This single rock, sitting silently for billions of years, may hold the faint whisper of an answer to one of humanity's most profound questions. That question, that shared sense of wonder, is a truly global phenomenon. It connects us across continents and time zones, a curiosity that persists whether this story finds you in the light of day or the dark of night. We invite you to share where you're listening from in the comments and to subscribe, ensuring you won't miss our future explorations. For to understand the monumental significance of this single, spotted rock, we must first trace the journey that led us to it. A journey that has taken us from blurry lenses in remote observatories to the tracks of robotic explorers crunching through alien dust 300 million miles away. It is the story of how our grand visions of Martian empires have given way to the search for something far smaller, yet infinitely more profound. And it is a story that truly began when one man, with a magnificent telescope and an even greater imagination, peered into the Martian twilight and believed he saw a civilization staring back. That man was Percival Lowell, a charismatic and wealthy Bostonian who, in the final decade of the 19th century, would forever intertwine the destiny of Mars with the search for intelligent life. He was not born an astronomer. He was a man of business, a diplomat, and a traveler, but his true passion was sparked by the work of an Italian astronomer named Giovanni Schiaparelli. In 1877, Schiaparelli had observed a series of faint, straight lines on the Martian surface, which he called canali. In Italian, the word simply means channels, natural formations, like the English Channel, but it was mistranslated into English as canals, a word that carried the unmistakable implication of artificial construction. This single, fateful mistranslation lit a fire in Lowell's imagination. He became convinced that these were not natural features, but the grand engineering works of an advanced Martian civilization. Possessed by this idea, and enabled by his considerable family fortune, he resolved to dedicate his life and resources to proving it. In the year 1894, he founded an observatory for the express purpose of studying Mars. He chose his location with scientific precision, a high mesa near Flagstaff, Arizona, at an altitude of over 2,100 meters, or about 7,200 feet, where the thin, dry, and stable air offered the clearest possible window to the heavens. There, he installed a magnificent 24-inch, or 61-centimeter, refracting telescope, a state-of-the-art instrument built by Alvin Clark and Sons, the finest telescope makers of the era. Night after night, year after year, Lowell would sit at the eyepiece, his eye pressed to the cold brass, waiting for those fleeting moments of perfect atmospheric stillness when the shimmering image of Mars would snap into sharp focus. In those moments, he saw more than just a ruddy, blurry disk. He saw a world. He meticulously drew what he observed, his hand transcribing the faint patterns of light and dark into intricate maps. The straight lines Schiaparelli had faintly glimpsed, Lowell saw in astonishing abundance and complexity. He charted hundreds of them, a vast, planet-spanning network of perfectly straight lines, some stretching for thousands of kilometers, or well over 1,000 miles, across the Martian surface. He observed that these lines invariably connected at darker, circular nodes, which he dubbed oases. To the skeptical eye, they were smudges at the limit of visibility, but to Lowell, they were the junctions and cities of a great civilization. From these detailed, almost obsessive observations, he wove a grand and compelling narrative, a theory so audacious and romantic, it seemed plucked from the pages of a novel. Mars, he argued, was a world far older than Earth. It was a dying planet, its surface having long ago lost its oceans and rivers to a relentlessly thinning atmosphere, turning it into a global desert. The inhabitants of this world, whom he imagined as an ancient, wise, and highly advanced race, were engaged in a desperate, planet-wide struggle for survival. Their brilliant engineers, he proposed, had constructed a colossal irrigation system on a scale dwarfing any human endeavor. This system, the canals he was observing, was designed to carry precious water from the Martian polar ice caps, which he correctly identified as shrinking and growing with the seasons, down to the parched equatorial regions where the last vestiges of their civilization clung to life in the cities he called oases. It was a beautiful, tragic, and heroic story. Lowell did not confine these ideas to the dry pages of academic journals. He became a tireless public advocate for his theory, publishing a trilogy of popular books, including the influential Mars and Its Canals in 1906 and Mars as the Abode of Life in 1908. He embarked on lecture tours, his eloquent and passionate presentations captivating audiences across America and Europe. He painted a picture of a world so vivid, so detailed, and so tantalizingly close that the public became utterly enthralled. The idea of Martians was no longer a fringe fantasy. It was a serious proposition from a credible man of science, presented with the full authority of his magnificent new observatory. His work had a profound cultural impact, providing the fertile imaginative soil from which a whole genre of science fiction would grow. H.G. Wells's The War of the Worlds, with its desperate Martian invaders, drew directly from Lowell's concept of a dying planet. Edgar Rice Burroughs's swashbuckling tales of John Carter on Barsoom, the Martian name for their world, were set against the backdrop of the dying canal cities Lowell had described. For the first time in history, Mars was not just a point of light or a subject of dry study. It was a real place in the public mind, a sister world populated with beings perhaps not so different from ourselves. Within the professional astronomical community, however, Lowell's theories were met with extreme skepticism. Many of his contemporaries, even those using telescopes of comparable or greater power, simply could not see the canals he drew with such certainty. They saw a few vague, streaky markings, some of which seemed to be real. But they saw nothing resembling the crisp, geometric network that filled Lowell's maps. The English astronomer E. W. Maunder, a noted solar and planetary observer, conducted experiments that demonstrated how the human eye and brain have a natural tendency to connect disparate, faint markings into straight lines, a form of optical illusion. Other critics suggested that the canals were merely an image of the blood vessels in Lowell's own eye, projected onto the featureless disk of the planet during long, strained hours of observation. The debate raged for years. The more Lowell insisted on the reality of his canals, the more isolated he became from the scientific mainstream. His most damning critic proved to be a new technology: photography. While the long exposure times required for astrophotography in that era could not capture the fine, low-contrast detail Lowell claimed to see, they also failed to show any evidence of the canals, suggesting the features were not there to be captured. Lowell remained undeterred, fiercely defending his vision of a civilized Mars until his death in 1916, convinced to his last day that he had been the first to discover and document the works of an alien intelligence. While history and more advanced science would ultimately prove his grand theory wrong, his legacy is far more complex than that of a simple failure. Percival Lowell, more than any other single individual, cemented Mars in our collective consciousness as a place of profound interest, a world that demanded exploration. He fired the public imagination and inspired generations of future scientists and engineers with his romantic, albeit flawed, vision. His passionate quest, born from a simple mistranslation, set humanity on a course for the Red Planet. He had asked the ultimate question: are we alone? And though his answer was wrong, the power of his question would propel us through the 20th century, past the limits of our own eyes and atmosphere, toward a much closer and far harsher view of the world he so desperately wanted to understand. The age of the telescope was ending, and the age of the rocket was about to dawn, arriving with a roar of chemical fire and the intense pressures of the mid-20th century. The first robotic emissaries aimed at Mars were not born of a pure, shared quest for knowledge, but were forged in the crucible of the Cold War, a technological and ideological contest between two superpowers, the United States and the Soviet Union. Getting to Mars first was not just a scientific goal. It was a demonstration of national power and intellectual supremacy. In the early 1960s, the Soviets made the first attempts, launching a series of probes that met with heartbreaking failure. Some were lost in launch explosions, others died in Earth orbit, and one, Mars 1, launched in 1962, successfully began its journey only to fall silent millions of kilometers from its destination. These early failures underscored the immense difficulty of the task. Interplanetary travel was a new and unforgiving frontier. The distances were almost incomprehensibly vast. The environment was hostile, and the engineering required a level of precision and reliability never before achieved. The challenge was taken up in the United States by NASA's Jet Propulsion Laboratory, or JPL, a sprawling campus of brilliant minds nestled in the dry foothills of the San Gabriel Mountains in Southern California. Under the direction of William Pickering, JPL had already succeeded with the Mariner 2 mission to Venus in 1962, and now their focus was fixed on the Red Planet. They designed a pair of identical twin spacecraft, Mariner 3 and Mariner 4, with the built-in redundancy that engineers call HOPE. The probes were compact, utilitarian machines, a world away from the romantic visions of Lowell. Each weighed just over 260 kilograms, about 575 pounds. Their magnesium frames, built into an octagonal structure sprouting 4 large solar panels like metallic wings. They were packed with instruments designed to deliver the first ever close-up measurements of Mars. A magnetometer to search for a planetary magnetic field, detectors for cosmic rays and charged particles, and an instrument to measure the density of the atmosphere. But the instrument that carried the weight of public expectation, the one that would truly succeed or shatter Lowell's legacy, was a simple, slow-scan Vidicon television camera, a primitive eye tasked with taking the first pictures of another planet from deep space. On November 5, 1964, Mariner 3 was launched, but its mission ended in minutes when the protective shroud covering the spacecraft failed to jettison, blinding its solar panels and dooming it to a useless solar orbit. The entire American Mars program now rested on the identical shoulders of its twin. 3 weeks later, on November 28, 1964, Mariner 4 sat atop an Atlas Agena rocket at Cape Kennedy in Florida. The launch was perfect. The spacecraft was hurled into the void on a precise trajectory, a 7.5-month, 523 million kilometer, or 325 million mile journey across the solar system. For 228 days, it flew in silence. Back at JPL, engineers and scientists in the control room, with their short-sleeved white shirts, narrow ties, and thick-rimmed glasses, watched the telemetry, the faint stream of data trickling back from their distant creation. They sent minor course corrections, monitored its health, and waited. The anticipation was immense. Despite the skepticism of professional astronomers, Lowell's vision of a canal-building civilization still held a powerful grip on the public imagination. No one truly expected to see cities, but many scientists held out hope for a world with a substantial atmosphere, perhaps with visible signs of vegetation or other large-scale features that could indicate a more clement, life-bearing environment. On the evening of July 14, 1965, the moment arrived. Mariner 4, now just a few thousand kilometers from Mars, began its encounter sequence. The television camera whirred to life, its lens pointed at the limb of the planet. It began capturing a series of 22 grainy, black and white photographs as it swept south across the terminator, the line between Martian day and night. The data transmission rate was agonizingly slow, a mere 8 1/3 bits per second, a technological whisper across the interplanetary void. It would take nearly 10 hours to transmit each individual image back to the massive radio dishes of the Deep Space Network. The impatient scientists at JPL, unwilling to wait that long for the official processed images, devised an ingenious workaround. They printed out the raw numerical data from the first image, a long string of zeros and ones representing the brightness of each pixel. And, using a color by numbers approach with pastel crayons on strips of paper, they hand-colored the world's first close-up portrait of Mars. As the colored strips were taped together on a wall, a picture began to emerge. It was not a picture of canals, oases, or seasonal vegetation. It was a picture of craters. The first image showed the curved edge of the planet against the black of space, its surface pockmarked and battered. It looked to the profound shock and disappointment of nearly everyone in the room, exactly like the moon. As the subsequent 21 images trickled in over the following week, the picture only grew bleaker. Craters upon craters, some ancient and worn down, others sharp and new, dominated the landscape. The photographs covered a swath of the planet, nearly 1% of its total surface area, and in all of it, there was not a single solitary feature that remotely resembled one of Lowell's canals. The romantic dream of a civilized, dying Mars did not fade. It was instantly and utterly obliterated by the hard, pixelated evidence. The other instruments delivered equally devastating verdicts. As the spacecraft passed behind the planet, the radio signal passed through the Martian atmosphere, allowing scientists to measure its density. The result was a crushing blow. The atmospheric pressure at the surface was, at most, 1% of Earth's, a near vacuum of thin carbon dioxide. This was far too thin to support liquid water on the surface, which would instantly boil away into vapor. It was too thin to provide any meaningful protection from ultraviolet radiation from the sun. The temperature readings confirmed a brutally cold world, with nighttime temperatures likely plunging below minus 100 degrees Celsius, which is roughly minus 148 degrees Fahrenheit. The magnetometer found no evidence of a global magnetic field or radiation belts, confirming that the surface was constantly bombarded by high-energy cosmic rays. Mars, as revealed by Mariner 4, was not a dying world. It was a dead world. It was geologically ancient, inactive, and profoundly hostile to life as we know it. The flyby was a spectacular engineering triumph, a landmark achievement in the history of exploration. But for many, it felt like a scientific funeral. The New York Times ran a headline declaring Mars a cosmic disappointment. The discovery fundamentally reset the scientific conversation. The question was no longer about intelligent life, but whether even the simplest microbial life could possibly survive in such a harsh environment. The grand, romantic visions of the 19th century had crashed headlong into the stark, unforgiving reality of the mid-20th century. Mars was cratered, cold, and seemingly barren. Yet, even in this profound disillusionment, the seeds of the next chapter of exploration were sown. The 22 images had only shown a tiny fraction of the planet. What secrets did the other 99% hold? Could Mars have been different in its distant past? The questions had changed, becoming more nuanced, more scientific, and more patient. The search for Martians was over, but the search for Mars was just beginning, and it would demand a new level of ambition, a mission that could do what no flyby ever could: touch the surface. In the wake of Mariner 4 and subsequent flybys by Mariners 6 and 7 in 1969, which reinforced the image of a cratered moon-like world, a consensus grew at NASA. The only way to truly understand Mars, to search for the faintest traces of life, past or present, was to land there. This was the genesis of the Viking program, arguably the most audacious and complex mission of robotic exploration ever conceived up to that point. It was a quantum leap beyond its predecessors. The plan was not to send one spacecraft, but two identical pairs, each consisting of a large, sophisticated orbiter and a lander capable of a soft, powered descent to the surface. It was a mission budget in the billions, a project involving thousands of scientists and engineers, all focused on a single, profound objective: to answer the question of life on Mars. Among the scientific teams, luminaries like the astronomer Carl Sagan played a pivotal role, not only in the scientific planning, but in capturing the public's imagination for this next great leap into the solar system. After years of design, construction, and testing, the journey began. On August 20th, 1975. Viking. 1 lifted off from Cape Canaveral atop a massive Titan 3E Centaur rocket, followed by its twin, Viking 2, on September 9th of the same year. Their 10-month, 800 million kilometer, or 500 million mile, voyage across the void was flawless, a testament to the meticulous engineering that went into their creation. In June of 1976, Viking 1's orbiter fired its main engine, slowing itself down to be captured by Martian gravity, becoming an artificial moon. For the next month, it circled the red planet, its cameras mapping the surface in unprecedented detail, searching for a safe and scientifically interesting place for its lander to attempt its perilous descent. The original landing site in a region called Kreisplanitia, or the Plains of Gold, had to be abandoned after the new high-resolution images revealed it was far more rugged and boulder-strewn than previously thought. A new, smoother site was chosen. The command was sent. On July 20th, 1976, a date deliberately chosen for its profound historical resonance as the 7th anniversary of the Apollo 11 moon landing, the Viking 1 lander separated from its orbiter. Encased in its protective aeroshell, it began its fiery plunge into the thin Martian atmosphere. For 3 hours, it fell. The heat shield glowed, enduring temperatures that would melt steel. At an altitude of about 6 kilometers, or just under 4 miles, a massive parachute deployed, snapping open to slow the craft from supersonic speeds. Soon after, the heat shield was jettisoned, and the lander's 3 legs extended, ready for contact. In the final moments, with the ground rushing up, retro rockets fired, a controlled explosion of hydrazine fuel that guided the lander to a gentle touchdown, kicking up a small cloud of red dust. Aboard the craft, a complex, automated sequence unfolded. Back at the Jet Propulsion Laboratory control room, the tension was unbearable. Due to the distance, the radio signals took a staggering 19 minutes to travel from Mars to Earth. The engineers and scientists could do nothing but watch their screens, waiting for a signal that would tell them if their creation had survived or if it had been dashed to pieces against the rocks. Then it came. A clear, strong signal. Viking 1 was safely on the surface of Mars. Cheers and applause erupted in the control room. Humanity had arrived. The first order of business was to look around. The lander's camera began a slow, deliberate scan. The first image was of one of the lander's own footpads, resting securely in fine-grained, reddish soil. Then, the camera panned up to the horizon. What it revealed was a scene of stark, beautiful, and profound desolation. It was a rolling plain of red rocks and fine sand stretching to a distant horizon under a pale, salmon-pink sky. The rocks were angular and pitted, likely volcanic in origin, scattered as if by an ancient flood. There was no sign of life, no plants, no creatures, not even a lichen clinging to a rock. A microphone designed to capture the sounds of Mars had failed, so the alien landscape was returned in an eerie silence. It was a world that was both utterly alien and strangely familiar, resembling the high deserts of Earth, yet fundamentally different. Now, the true work could begin. The centerpiece of the Viking lander was a sophisticated, automated miniature laboratory, a 40-kilogram or 90-pound marvel of engineering designed to perform 3 distinct biological experiments. A robotic arm, stretching nearly 2 meters, or about 6 feet, scooped up a sample of the Martian soil and deposited it into a hopper on the lander, which then distributed the material to the 3 experiments. The first was a gas chromatograph mass spectrometer, or GCMS. Its job was straightforward: to search for organic molecules, the carbon-based compounds that are the essential building blocks of all known life. The soil was heated to high temperatures to vaporize any organic material, which would then be identified by the instrument. The result was a profound shock. The GCMS found nothing: no amino acids, no hydrocarbons, no complex polymers. To the limits of its very high sensitivity, the Martian soil was completely devoid of organics. This was not just a disappointment. It was a deep scientific puzzle. Even meteorites that fall to Earth contain organic compounds. The soil on the Moon, which is sterilized by unfiltered solar radiation, has more organics from cosmic dust than what Viking found. It suggested that something on the Martian surface was actively destroying these molecules. The second experiment was the gas exchange experiment. It took a sample of soil and added a complex nutrient broth, a sort of chicken soup for microbes, and then monitored the air above the sample to see if any gases indicative of metabolism, like carbon dioxide or oxygen, were released. It registered a positive result almost immediately. A significant amount of oxygen was released from the sample. However, the same result occurred in a control run, where the sample was first heated to sterilize it, and it also happened when plain water was used instead of the nutrient broth. This pointed not to life, but to a strange, hyper-reactive soil chemistry. Scientists concluded that highly oxidizing compounds in the soil, perhaps peroxides or superoxides created by the intense ultraviolet radiation, were reacting with the water in the nutrient mix and releasing the oxygen. It was an imitation of life, but a purely chemical one. Then came the third experiment, the one that would create a controversy that lingers to this day: the labeled release experiment, conceived by a scientist named Gilbert Levin. Its design was elegant. A small sample of soil was moistened with a drop of nutrient solution. Crucially, the carbon atoms in this nutrient were a radioactive isotope, carbon-14. The hypothesis was that if microorganisms in the soil consumed the nutrients, they would release waste gases containing the radioactive carbon, which would be detected by a radiation counter. When the experiment was run, the result was immediate and dramatic. The radiation detector showed a steep spike in radioactive gas, exactly what one would expect to see from a thriving colony of microbes metabolizing the food. The data curve looked biological. To be sure, a control experiment was performed on a second soil sample, which was first heated to 160 degrees Celsius, or 320 degrees Fahrenheit, to kill any potential life. This time, when the radioactive nutrient was added, nothing happened. The signal was flat. This result, a positive signal that was nullified by sterilization, was a textbook definition of a positive result for life. The mission now faced a deep and troubling contradiction. The labeled release experiment had met all the pre-launch criteria for the detection of life. Yet, the GCMS insisted that the soil contained none of the building blocks necessary for life to exist. How could there be a biological process without the biological molecules? Faced with this paradox, NASA had to make an official judgment. The scientific consensus, led by the mission leaders, landed on the side of caution. They concluded that the lack of organic molecules was the definitive result. The positive signal from the labeled release experiment, they argued, must also be the result of an exotic, non-biological chemical oxidant in the soil that was simply mimicking a life sign, a chemical so reactive that it broke down the nutrients and released the radioactive carbon. While the majority of the scientific community accepted this conclusion, Gilbert Levin did not. He spent the next 4 decades until his death passionately arguing that his experiment had indeed discovered microbial life on Mars, and that the GCMS had simply not been sensitive enough or had been foiled by the strange soil chemistry. The Viking missions were a spectacular success, providing a treasure trove of data that would shape our understanding of Mars for decades. But on the ultimate question, they delivered a profound and tantalizing ambiguity. Mars was not the simple, dead world Mariner 4 had shown us. It was a world of complex, reactive, and mysterious chemistry. The Viking enigma left humanity in a state of scientific limbo. We had reached out to touch the face of another world and asked it the greatest of all questions, only to receive a riddle in reply. That riddle would echo through the halls of science for 2 decades, a period of profound reflection and strategic reevaluation for the entire Mars exploration community. The Viking missions, for all their technological brilliance, had revealed a fundamental flaw in the approach. Attempting to find life directly, with only a few scoops of soil from 2 isolated locations, was like dropping a bucket into the Pacific Ocean, pulling it up empty, and declaring there are no whales. The Martian surface was vast, and its history was deep. The ambiguity of the Viking results made it nearly impossible to justify another multi-billion-dollar mission to simply repeat the same biological experiments. A new strategy was needed, a paradigm shift that moved away from the tantalizing but perhaps premature search for extant life and toward a more foundational, more patient question. Was Mars ever a habitable world? This new approach was distilled into a simple, powerful, and scientifically elegant mantra that would guide the next generation of exploration. Follow the water. The logic was undeniable. On Earth, from the deepest volcanic vents to the most arid deserts, wherever we find liquid water, we find life. Water is the one non-negotiable ingredient for life as we know it. Therefore, before searching for the faint biological signature, the first step must be to search for the geological fingerprints of water in Mars's distant past. If it could be proven that Mars once hosted persistent bodies of liquid water, lakes, rivers, perhaps even oceans, then the case for it, having been a cradle for life, would become immeasurably stronger. The long hiatus in Mars landings finally ended in the 1990s with a renewed wave of exploration, this time beginning from orbit. In 1997, NASA's Mars Global Surveyor spacecraft arrived, a mapping mission designed to paint a comprehensive new portrait of the planet. Armed with a suite of advanced instruments, it orbited Mars for nearly a decade, revolutionizing our understanding of its surface. Its Mars Orbiter camera, with a resolution far exceeding anything that had come before, revealed a landscape crisscrossed with the undeniable remnants of ancient river channels, deltas, and alluvial fans. These were not optical illusions or wishful thinking. They were vast, complex hydrological systems carved into the terrain, clear evidence that colossal amounts of water had once flowed across the surface. The spacecraft's Mars Orbiter Laser Altimeter, or MOLA, bounced laser beams off the planet to create a breathtakingly precise three-dimensional map of the entire globe. This map confirmed that the northern third of Mars was a vast, smooth basin, several kilometers lower in elevation than the cratered southern highlands, lending strong support to the theory that a massive ocean may have once filled this depression. Perhaps most tantalizingly, Mars Global Surveyor spotted what appeared to be fresh gullies on the steep inner walls of some craters and valleys. They looked startlingly like features on Earth carved by flash floods, raising the electrifying possibility that liquid water might not be confined to the ancient past, but could perhaps still seep to the surface in transient bursts today. Building on this success, the 2001 Mars Odyssey orbiter arrived with a different set of tools. Its primary mission was to map the chemical composition of the surface. One of its instruments, a gamma-ray spectrometer, was designed to detect the chemical elements in the top meter, or roughly 3 feet, of the Martian soil. It did this by measuring the characteristic energies of gamma rays and neutrons emanating from the surface. The instrument soon made a landmark discovery. In the high latitudes of both the northern and southern hemispheres, it detected a massive abundance of hydrogen. There was only one plausible explanation for so much hydrogen hiding just beneath the Martian dust: vast quantities of water ice. This was not a small amount. The data indicated enough frozen water to fill Lake Michigan twice over. The water was there, just locked away as permafrost in a global deep freeze. The evidence from orbit was compelling, even overwhelming. Mars was not born a dry world. It had once been a water world. But orbital data, however persuasive, is still remote. To truly confirm the story, to close the case, humanity needed to go back down to the surface and become a field geologist. This was the task assigned to the Mars exploration. Rovers, Spirit and Opportunity, twin six-wheeled, solar-powered robots designed to be our eyes, hands, and analytical tools on the ground. Launched in 2003, their mission was to land in places specifically chosen from the new orbital. Maps, because they seemed to have been shaped by water. Spirit was sent to Gusev Crater, a 166-kilometer or 103-mile wide basin that appeared to be an ancient, dried-up lakebed. Opportunity's destination was a flat, smooth plain on the opposite side of the planet called Meridiani Planum, chosen because orbiters had detected a high concentration of crystalline hematite, an iron oxide mineral that, on Earth, almost always forms in the presence of liquid water. On January 25, 2004, after a hair-raising descent cushioned by a cocoon of giant airbags, Opportunity bounced to a stop and deflated its protective shell. By a stroke of incredible luck, the rover had rolled to a halt inside a small, shallow impact crater, only 22 meters or 72 feet in diameter. And exposed in the inner wall of this small crater was an outcrop of layered bedrock, the first that any mission had ever been able to examine up close. It was a geologist's dream. The science team, ecstatic, immediately directed Opportunity to approach the rock. What it found in that outcrop, which they named Opportunity Ledge, would be written into the history books of planetary science. Using the instruments on its robotic arm, a microscopic imager, and a suite of spectrometers, the rover began to piece together the story written in the stone. The first clue was the physical structure of the rock itself. It was clearly sedimentary, laid down in fine layers. Some of these layers were curved and angled in a pattern known as cross-bedding, a distinctive signature left by sand ripples formed at the bottom of a gentle, flowing body of water. Then came the composition. Embedded within the rock layers, like blueberries in a muffin, were millions of tiny, spherical concretions, rich in hematite. These blueberries, as the team nicknamed them, were evidence of water having percolated through the rock long ago, causing minerals to precipitate out and form these BB-sized spheres. Examining the rock's chemistry, Opportunity's spectrometers found it was incredibly rich in sulfur and salts, particularly a mineral called jarosite. On Earth, jarosite is a smoking gun mineral. It forms only through the evaporation of acidic, salty water. Finally, the microscopic imager revealed tiny tabular holes, or vugs, within the rock. These were the ghosts of former crystals, likely salt crystals, that had formed within the rock and later dissolved away as the water chemistry changed. Each piece of evidence, on its own, was suggestive. But taken together, the story was undeniable and unambiguous. Opportunity was parked on the shoreline of what was once a vast, shallow, and salty sea. This was not a flash flood or a transient trickle. This was a persistent, stable body of liquid water that had existed on the surface of Mars for a substantial period of time. The rover's 90-day primary mission was a resounding success, and it would go on to explore for nearly 15 years, traveling over 45 kilometers, or 28 miles, and building an ever more detailed picture of this ancient aqueous environment. The follow the water strategy had been triumphantly vindicated. The image of Mars was transformed once again. It was not Lowell's civilized, dying world, nor was it the sterile, moon-like rock of Mariner 4, or even the chemically enigmatic desert of Viking. It was a world with a dynamic, watery past, a world that had once possessed all the necessary ingredients for life. The question was no longer if Mars was ever habitable. The question now was where, on that once habitable world, could we find the best preserved records of that ancient environment and of any life that might have called it home. That question became the central challenge for NASA in the decade following the triumphs of Spirit and Opportunity. The paradigm had shifted from a binary search for life to a more nuanced geological investigation. The new goal was not merely to find a habitable environment, but to find the perfect habitable environment. A place that not only could have supported life billions of years ago, but that also possessed the specific geological characteristics needed to preserve the delicate chemical or morphological traces of that life, the biosignatures over the vast gulf of geologic time. This monumental task required a new kind of explorer, a rover that would be a significant evolutionary leap beyond its predecessors. This mission, conceived as Mars 2020 and later christened Perseverance, would be the most sophisticated robotic geologist ever sent to another world. It was a behemoth, the size of a small sport utility vehicle, weighing over 1,000 kilograms, or roughly 2,200 pounds, and powered not by solar panels, but by a radioisotope thermoelectric generator, a nuclear battery that would give it the freedom to operate through harsh Martian winters and dust storms. At its heart, Perseverance was designed to be an astrobiologist, while Spirit and Opportunity had been tasked with confirming the presence of past water. Perseverance's job was to seek the signs of past life within the rocks formed by that water. To do this, it was equipped with a suite of 7 groundbreaking instruments. On its mast, a device called SuperCam could fire a laser at a rock from 7 meters, or about 23 feet away, vaporizing a tiny portion of it and analyzing the resulting plasma to determine its chemical composition. On its robotic arm, two instruments named Pix-L and Sherlock would work in tandem. Pix-L, the planetary instrument for X-ray lithochemistry, could map the elemental composition of a rock at a microscopic scale, while Sherlock, the scanning habitable environments with Raman and luminescence for organics and chemicals, would use its own laser and spectrometer to create fine-scale maps of minerals and, crucially, organic compounds. This was the 1-2 punch the Viking mission had lacked: the ability to find organic molecules and immediately see their geological context, to understand how they were preserved and distributed within the rock. But the rover's most important capability, the very reason for its existence, was its sample caching system. Perseverance was not designed to be the final arbiter of life on Mars. Instead, it was to be the first leg of an unprecedented interplanetary relay race. It carried 43 pristine sample tubes, and its core mission was to use a rotary drill on its arm to extract pencil-sized cores of the most promising Martian rocks, seal them in the tubes, and deposit them on the surface for a future mission to retrieve and return to Earth. The scientific community understood that the ultimate verdict would likely require the full analytical power of laboratories back on our own planet. With such a capable explorer, the question of where to send it became the most critical decision of the entire mission. The landing site selection process was a long and intensely debated affair, lasting for more than 5 years and involving scientists from all over the world. More than 60 potential locations were proposed and meticulously studied using years of orbital data. Each site had its champions and its scientific merits, from ancient hot springs to the exposed layers of deep canyons. But as the choices were narrowed down, one candidate consistently rose to the top of the list: a 45-kilometer, or roughly 28-mile, wide impact crater in a region known as the Nili Fossae, a crater named Jezero. The word Jezero means lake in several Slavic languages, a name that perfectly captured its scientific allure. Orbital imagery of Jezero was not just promising, it was breathtaking. It showed a crater that was once clearly filled with a deep, calm body of water, a paleo lake that may have existed for millions of years. Even more compelling were the features on its western rim. There, a distinct and beautifully preserved river delta fanned out into the crater floor. The images were so clear that scientists could trace the meandering path of the ancient river that had breached the crater wall and flowed into the nascent lake. This was the environment astrobiologists had dreamed of. A river delta is one of the best places on Earth to preserve signs of life. As the river flowed into the still water of the lake, its current would have slowed, causing it to drop its payload of sediment. This process, happening over countless millennia, would have gently buried and preserved anything that was living in the water column or on the lake floor, including any microscopic organisms. The fine-grained clays and mudstones that form in such an environment are exceptionally good at shielding delicate, organic molecules from harsh radiation. Furthermore, as the climate on Mars changed and the lake began to dry up, its shoreline would have retreated. This process would have created a bathtub ring of minerals around the edge of the crater, potentially concentrating and entombing evidence of microbial life in deposits like carbonates. On Earth, carbonate minerals are famous for preserving ancient microbial structures known as stromatolites. The scientific case was overwhelming. If life ever existed on Mars, Jezero Crater was one of the most likely places to find its signature. But there was a catch. Jezero, for all its scientific promise, was a landing site designer's nightmare. The very features that made it so compelling, the cliffs of the delta front, the fields of sand dunes, the jumbles of boulders washed in by the ancient river, made it an exceptionally dangerous place to land. The landing ellipses for previous missions were large, forgiving ovals, but Perseverance had to be threaded into a specific, narrow patch of safe terrain within this hazardous environment. To achieve this, NASA deployed a revolutionary new landing system. The rover would still use the familiar heat shield and parachute, but the final descent was controlled by a jet-powered sky crane that would hover above the surface and gently lower the rover to the ground on a set of cables. The critical new technology was called terrain relative navigation. During its final descent, Perseverance would take pictures of the rapidly approaching ground, compare them in real time to an onboard map of known hazards, and autonomously divert its course to a safe landing spot. This seeing eye technology was essential for the mission's success. On July 30th, 2020, Perseverance began its journey, launching from Cape Canaveral. After a voyage of 203 days and 472 million kilometers, or 293 million miles, it reached Mars. On February 18th, 2021, the world watched as the spacecraft plunged into the Martian atmosphere at nearly 20,000 kilometers per hour, or about 12,000 miles per hour. The 7 minutes of terror that followed were a flawlessly executed dance of engineering. The heat shield glowed, the parachute deployed, and in the final minute, the sky crane took over, its terrain relative navigation system guiding it away from a dangerous rocky patch. It hovered, lowered the rover on its tethers, and as soon as Perseverance's wheels touched the ground, the cables were cut and the sky crane flew off to crash a safe distance away. A voice in mission control at JPL announced the words the world had been waiting to hear. Touchdown confirmed. Perseverance safely on the surface of Mars. The promised land had been reached. Now, the search could begin. That search did not start with a triumphant sprint to the distant delta, but with a period of meticulous, deliberate caution. For weeks after its landing on February 18th, 2021. Perseverance was a creature of patience, slowly waking up in its new alien home. On Earth, at the Jet Propulsion Laboratory, hundreds of scientists and engineers, their lives now tethered to the Martian clock, worked through the rover's commissioning phase. They sent the commands that unfurled its robotic arm, a complex limb nearly 2 meters, or about 7 feet, long, flexing its joints and testing the grip of its turret of instruments. They raised its remote sensing mast, the head and neck of the rover, which swiveled to capture its first breathtaking 360-degree panoramas of the Jezero landscape. Those first images revealed a world of profound stillness, a flat, rock-strewn plain under a butterscotch sky, with the eroded rim of the crater visible on the distant horizon, and to the west, the tantalizing layered front of the ancient river delta, the mission's ultimate prize. The initial campaign, however, was focused on understanding the immediate surroundings, the crater floor itself. The scientific consensus before landing had been that the floor would be composed of sedimentary rock, the muddy bottom of the ancient lake. But as Perseverance began its first tentative drives, its wheels crunching over the red soil, and as it used its instruments to abrade and analyze the local bedrock, it revealed a surprise. The rocks of the crater floor were not sedimentary at all. They were igneous, volcanic in origin. This was a profound discovery. It meant that after the lake in Jezero had dried up, volcanic lava had flowed across the crater floor, completely burying the original lake bed sediments. This was not a setback, but a crucial new piece of the planet's history. And the team spent its entire first year methodically exploring and sampling these volcanic rocks, which would themselves provide a vital timeline for the region's geological evolution. But the delta still beckoned. In the spring of 2022, Perseverance finished its crater floor campaign and turned its wheels west, embarking on the long journey to the delta front. This was a trek of over 5 kilometers, or about 3 miles, across treacherous terrain. To speed up the process, the rover drivers on Earth began to rely more and more on the rover's sophisticated auto-navigation system, or AutoNav. They would plot a general course, and the rover's own computer brain would analyze stereoscopic images of the path ahead, intelligently weaving its way around impassable boulders and dangerous sand traps, sometimes driving for hours with minimal human intervention. Slowly, methodically, the landscape began to change. The flat volcanic plains gave way to rolling hills and ridges. The first sedimentary layers deposited at the farthest edge of the ancient lake. Perseverance was driving up the timeline, moving from the newer volcanic rock onto the older water-lane deposits of the delta. By the summer of 2024, the rover had reached its new area of operations, the very edge of an ancient, winding river channel that had once fed the lake, a feature named Neretva Vallis. Here, the geology was a complex jumble of sandstone and mudstone, rocks formed from the grit and silt that had been carried by the flowing water and then settled out. The science team on Earth would start each Martian day, or Sol, by poring over the latest images sent back by the rover's mast-mounted cameras, scrutinizing every rock in the forward-looking vista, searching for a target worthy of close inspection. In the early days of July, a particular rock caught their eye. It was located on a small, eroded mound that the team had nicknamed Mount Washburn. The rock itself was about 1 meter wide, roughly 3 feet, and had a distinctive, almost arrowhead shape. It was lighter in color than its surroundings and seemed to display a peculiar, mottled texture. Intrigued, the team directed Perseverance to approach it. As the rover drew closer, the rock's unique character became even more apparent. It was a piece of sandstone, but it was crisscrossed with brighter veins and dotted with strange, dark patches. Following a naming convention that linked features in the area to national parks and monuments in the United States, the team christened this intriguing target Cheyava Falls, after a spectacular waterfall in the Grand Canyon of Arizona. The name, with its evocation of flowing water, would prove to be more apt than they could have possibly imagined. The commands were sent across the interplanetary void. Perseverance maneuvered its long robotic arm with millimeter precision, positioning its turret of instruments just centimeters away from the rock's surface. The first step was to use the gas dust removal tool to blow away the fine layer of red dust that coated everything, revealing the rock's true, unweathered face. Then, the instruments went to work. The microscopic imagers on Sherlock and Pixel began scanning, acting as the rover's geological hand lens. As the data began to stream back to Earth, relayed through orbiters circling high above, the science team gathered at their monitors, their quiet anticipation turning to focused excitement. The close-up images were stunning. The surface of Cheyava Falls was unlike anything they had ever seen on Mars. The rock was composed of 2 main components. The bulk of it was a reddish material, which the team suspected was hematite, the same iron-rich mineral that Opportunity had found. Running through this reddish matrix were bright white veins, identified as calcium sulfate, a mineral that precipitates from water. Clear evidence that fluid had once coursed through fractures in this rock. But it was the other features that made everyone lean closer to their screens. The rock was covered in 2 types of unusual, dark, circular patterns. The first were larger, irregular splotches, up to 1 centimeter, or nearly half an inch, in diameter, which the team began calling leopard spots. The second were smaller, more numerous, and perfectly spherical, each only about 1 millimeter across. These they nicknamed poppy seeds. They were embedded within the rock, a part of its fundamental structure. This was not a surface stain or a trick of the light. The strange patterns, the spots and the seeds, were an intrinsic part of the stone's very fabric, a record of the chemistry and environment in which it had formed billions of years ago. The initial visual inspection had raised 1,000 questions. It had presented the team with a geological puzzle so strange, so unlike the more uniform rocks they had studied before, that it demanded a new and far more profound explanation. That new and profound explanation would not come from a single glance, but from a painstaking deconstruction of the rock's every feature, a process of reading the stone layer by layer, mineral by mineral. The science team on Earth, now acting as remote, robotic field geologists, began to command a carefully choreographed ballet of instruments, each designed to interrogate a different aspect of Cheyava Falls's enigmatic character. The first step was to move beyond the wide-angle views of the mast cameras and get a true geologist's hand lens perspective. On the turret at the end of Perseverance's robotic arm is an instrument called Watson, short for the Wide-Angle Topographic Sensor for Operations and Engineering. Despite its engineering-focused name, Watson is the mission's microscopic imager, capable of taking incredibly detailed, full-color pictures of rock textures, essentially placing the science team's eyes just inches from the Martian surface. The arm whirred into position, delicately placing the instrument over the area of interest. A ring of white light-emitting diodes, or LEDs, flashed on, illuminating the rock's surface and banishing the shadows of the Martian morning. The resulting images, streamed back to Earth, were revelatory. Under Watson's unblinking gaze, the textures resolved into a rich and complex tapestry. The reddish host rock was confirmed to be a sandstone, its individual grains of sand, cemented together over eons, clearly visible. This in itself told a story of grit and sediment carried along by the currents of the Neretva Vallis River channel and deposited here at the edge of the great Jezero Lake. The brilliant white veins that cut through this sandstone were shown to be crystalline, their structure confirming they were minerals that had grown within fractures in the rock, a clear sign that water had continued to flow and percolate through this formation long after it had been buried and turned to stone. This was a place that had been wet not just once, but multiple times, its history steeped in water. But it was the dark spots and seeds that commanded the most attention. Under microscopic view, they were even more peculiar. The larger leopard spots, some as wide as 1 centimeter, or about 4/10 of an inch, were not mere surface stains. They had a distinct three-dimensional structure, their material appearing coarser and more granular than the surrounding sandstone. They were clearly a different phase of material, embedded within the host rock like aggregates in concrete, yet they showed no signs of being pebbles that were simply washed in with the sand. Their irregular, but clearly defined boundaries suggested they had formed in situ, precipitating directly out of the water that saturated the original sandy sediments. Even more intriguing were the poppy seeds. These tiny spheres, just a millimeter, or about 4/100ths of an inch, across, were almost perfectly round. In geology, such perfect spherules are rarely accidental. They are often concretions, formed when minerals in a water-rich solution precipitate and grow outwards from a central nucleus, a process that naturally favors a spherical shape. They were reminiscent of the hematite blueberries that the Opportunity rover had discovered 2 decades earlier, but these were a different color, a different texture, and embedded in a completely different type of rock. Taken together, the visual evidence from Watson painted a picture of a dynamic chemical environment in Mars's ancient past. It allowed the scientists to reconstruct a likely sequence of events. First, sand was deposited by the river. Then, this sand was saturated with iron-rich water, which cemented the grains together and formed the hematite-rich sandstone matrix. Sometime during or after this process, a change in the water's chemistry occurred, creating localized conditions that caused the minerals of the leopard spots and poppy seeds to form and crystallize within the wet, porous rock. Finally, after the rock had hardened, it was fractured, perhaps by geologic stresses or an impact event, and a later generation of water with a different chemical makeup flowed through these cracks, depositing the veins of pure calcium sulfate. Chayava Falls was not just a rock. It was a historical document, a preserved record of multiple, distinct chapters in the story of water at Jezero Crater. The structure, texture, and relationships between its various parts were a form of language, a story told in minerals instead of words. And this story was leading toward a tantalizing climax. The very presence of such complex, chemically segregated features hinted at a place of intense chemical activity. The boundaries between the spot and the surrounding matrix would have been zones of sharp chemical gradients, places where different molecules with different energy levels were in close proximity. On Earth, such chemical gradients are hotspots for microbial life. Microbes are the ultimate chemical opportunists, and many types have evolved to live by exploiting the energy differential between 2 different minerals in contact with each other. They essentially eat the chemical energy of the rock. The strange mottled appearance of Chayava Falls, therefore, was more than just a geological curiosity. It was a potential signpost for a past habitable environment on a microscopic scale. It represented exactly the kind of place where, if life ever arose on Mars, it might have found a foothold, a place with water, a complex mix of minerals, and most importantly, a potential source of chemical energy to fuel a metabolism. The visual inspection had provided the context, revealing the intricate stage upon which a chemical drama had played out. But it could not name the actors. The fundamental question remained: what precisely were the leopard spots and poppy seeds made of? Unlocking their elemental and molecular composition was the critical next step. Only by identifying the specific chemicals concentrated in these strange patterns could the science team begin to understand the reactions that formed them, and whether those reactions could have provided the energy needed to support life. The stage was set for the rover's most powerful analytical tools to peer inside the rock's chemical soul, to translate its silent mineral language into the universal syntax of the periodic table. The first instrument to take on this task was PIXL, the planetary instrument for X-ray lithochemistry. Mounted on the rover's turret, PIXL is a masterpiece of miniaturization, a device that performs its work with a delicate, almost intimate proximity to its target. The robotic arm maneuvered the turret until PIXL's sensor head hovered less than a centimeter, just a fraction of an inch, above the surface of Chayava Falls. From this vantage point, the instrument fired a hair-thin beam of X-rays at the rock. When these X-rays strike the atoms in the rock, they knock electrons out of their orbits, and as other electrons fall to fill the gaps, they emit their own X-rays at energies that are a unique, telltale fingerprint for each specific chemical element. By slowly scanning its beam back and forth, PIXL can build up a hyper-detailed map of the elemental composition of the surface, revealing not just what elements are present, but precisely where they are located, pixel by pixel. The data began to build, line by line, on the screens back at the Jet Propulsion Laboratory. What emerged was a chemical map that was as textured and complex as the rock's physical appearance. The reddish sandstone matrix was, as expected, rich in silicon, oxygen, and iron, the basic components of sand cemented by hematite. The bright white veins glowed in the map's channels for calcium and sulfur, confirming they were calcium sulfate. But when PIXL focused on the enigmatic leopard spots and poppy seeds, the chemical map lit up with astonishing intensity. The first major discovery was iron. The dark spots were not just a little richer in iron. They were overwhelmingly concentrated in it, showing a concentration far higher than the surrounding hematite-rich rock. This was a critical clue, suggesting that whatever process formed these features was exceptionally efficient at gathering iron from the water and depositing it in these localized zones. But it was the second discovery that truly electrified the science team. As PIXL mapped the other elements, it found that the iron-rich spots were also packed with phosphorus. Specifically, they were rich in phosphate, a molecule that binds a phosphorus atom to 4 oxygen atoms. The correlation was undeniable. Wherever the iron was concentrated, so was the phosphate. On Earth, this connection is profound. Phosphate is the absolute linchpin of life. It forms the structural backbone of our DNA and RNA, the molecules that carry our genetic code. It is a critical component of our cell membranes, the very walls that separate a living organism from its environment. And it is the key ingredient in adenosine triphosphate, or ATP, the universal energy currency of every known living cell. Life on Earth runs on phosphate. To find iron and phosphate, two elements so deeply intertwined with biological processes, packed together in these strange, specific structures, was a discovery of the highest order. It suggested a chemical system of remarkable complexity. Now, the investigation moved to the molecular level. PIXL had provided the elemental ingredients list, but Sherlock, the scanning habitable environments with Raman and luminescence for organics and chemicals, was needed to see how those ingredients were assembled. Sherlock operates on a different principle. It shines a focused beam of ultraviolet laser light onto the rock. Most of that light simply scatters back, but a tiny fraction of it interacts with the molecules in the rock, causing them to vibrate and re-emit the light with a slightly different energy. This subtle shift, known as Raman scattering, is a unique fingerprint for specific molecules and mineral structures. Sherlock's primary target was one of the most fundamental of all: organic molecules, the carbon-based compounds that are the stuff of life. The arm positioned Sherlock to scan across the boundary of one of the leopard spots. The laser began its work, mapping the molecular landscape. The results were the final, crucial piece of the puzzle. Sherlock detected the distinct spectral signatures of organic compounds. This was not the first time organics had been found on Mars. The Curiosity rover had detected them years earlier in mudstone from a different crater. But the context here was everything. The organics discovered by Sherlock were not just loosely scattered in the soil or uniformly distributed in the rock. Instead, their signatures were strongest inside the leopard spots, spatially correlated with the high concentrations of iron and phosphate that PIXL had just mapped. The implications of this convergence were staggering. The science team now had 3 independent, overlapping lines of evidence, all pointing to the same conclusion. They had found high concentrations of iron. They had found high concentrations of phosphate, life's most critical building block. And they had found organic molecules, the raw material of life itself, all packaged together in the same microscopic location within the rock. This was no longer just a collection of interesting minerals. It was a coherent chemical system. From this nexus of data, a powerful and compelling hypothesis began to form. The leopard spots were likely zones where iron in the ancient Martian water was undergoing a chemical change, a process known as oxidation and reduction, or redox. The interface between these iron-rich spots and the surrounding water-saturated rock would have created a sharp electrochemical gradient, a kind of natural battery on a microscopic scale. This is precisely the kind of energy source that chemosynthetic microbes on Earth exploit. On our own planet, in dark places where sunlight cannot penetrate, such as deep-sea hydrothermal vents or deep within the Earth's crust, there are entire ecosystems of microbes that live by harnessing the energy from chemical reactions between minerals and water. They eat rocks, using the energy from redox reactions to power their metabolisms. The scientists began to imagine the ancient environment at Cheyava Falls. Water, rich with dissolved minerals, percolates through the porous sandstone. Within this rock, localized zones begin to concentrate iron and phosphate. This process creates a chemical disequilibrium, an energy source. If primitive microbes existed in that water, they would have been drawn to this energy-rich zone. Here, they would have found everything they needed to thrive, an energy source from the iron chemistry, and a crucial nutrient and building material in the abundant phosphate. The organic molecules detected by Sherlock could be the fossilized remnants of these very microbes, their cellular machinery preserved for billions of years. Alternatively, they could be the raw organic material that was present in the water, which became concentrated in these chemically active zones, providing the feedstock that could have led to the origin of life itself. The Cheyava Falls rock was no longer just a geological curiosity. It had become the most complete potential biosignature ever discovered. It presented a self-contained story, a recipe for life. It had the water, it had the essential ingredients in phosphate and organics, and most importantly, it had a plausible energy source, the spark, all co-located in a single, preserved geological context. It was not yet proof of life, but it was a detailed blueprint for how life could have existed in that exact spot. A blueprint that now demanded the most rigorous scrutiny science could offer. That blueprint, as compelling and coherent as it was, immediately ran headlong into one of the most rigorous and cautious doctrines in all of science: the extraordinary burden of proof required for any claim related to extraterrestrial life. Carl Sagan, one of the original visionaries of the Viking mission, had famously popularized the maxim, "Extraordinary claims require extraordinary evidence." For the scientists at NASA, this is not just a memorable phrase. It is the foundational principle that governs the entire field of astrobiology. The history of the search for life on Mars is littered with cautionary tales, from Percival Lowell's Canals to the still debated results of the Viking-labeled release experiment. Each episode has reinforced a crucial lesson. Nature, and especially Martian chemistry, is full of surprises and has an uncanny ability to mimic the signs of life through purely non-biological processes, what scientists call abiotic processes. A pattern that looks like a fossil can be a strangely shaped mineral crystal. An organic molecule can be delivered by a meteorite or formed through geological reactions. A chemical signal that seems to indicate metabolism can be the product of an exotic, hyper-reactive soil. To avoid these pitfalls and to bring a common, structured approach to any future discoveries, NASA had in recent years developed a formal framework for evaluating potential biosignatures. This framework is known as the Confidence of Life Detection, or CoLD scale. It is a 7-step ladder of scientific certainty, a methodical, step-by-step process designed to guide research and manage expectations, both within the scientific community and for the public. Step 1, at the very bottom of the ladder, is the detection of a signal of potential biological relevance, a hint that something warrants a closer look. Step 7, at the very top, represents universal scientific consensus that definitive evidence of life has been found, and all possible non-biological explanations have been exhaustively ruled out. The CoLD scale is deliberately designed to be difficult to climb. Moving up a single step requires new, independent lines of evidence and the systematic elimination of abiotic mimics. When the Perseverance team announced their findings from Chayava Falls in the late summer of 2024, they were extremely careful and deliberate in their language. They placed their discovery squarely and conservatively at step 1. Chayava Falls was, they stated, a potential biosignature. The combination of an energy source, organic molecules, and phosphates was a tantalizing and unprecedented discovery, but it was still just a signal. The immediate task, before even considering a move to step 2, was to begin the exhaustive process of interrogating that signal, of playing devil's advocate against their own most exciting hypothesis. The first major challenge was to rule out the possibility that the organic molecules Sherlock had detected were not native to Mars at all, but were contaminants brought from Earth. Perseverance is arguably the most atomically clean machine humanity has ever built. It was assembled in a specialized clean room at the Jet Propulsion Laboratory under the strictest of protocols. Engineers wore head-to-toe bunny suits, and every single component was sterilized, baked, and cleaned with alcohol wipes to minimize its biological and organic burden. But it is impossible to be perfect. The rover still carries a faint trace of Earth with it. To account for this, Perseverance is equipped with witness tubes, special sample tubes, that were opened to the Martian atmosphere to collect any contaminants that might be outgassing from the rover itself. Analyzing these witness samples would be a key step. More importantly, the team needed to demonstrate that the organics were concentrated specifically within the leopard spots and not found in the surrounding rock or in other geologically different formations. This spatial correlation, which Sherlock's data strongly suggested, was the best line of defense against a contamination argument, as terrestrial contaminants would likely be more randomly and evenly distributed. The next, and far more difficult challenge, was to brainstorm every conceivable non-biological way that nature could have created the features seen in Cheyava Falls. Could the iron and phosphate have been concentrated by a purely geological process, like the slow evaporation of a specific type of groundwater known as diagenesis? Could the organic molecules have been formed by reactions between water and volcanic minerals, a process known as Fischer-Tropsch synthesis, and then become concentrated in the same spots as the other minerals? These abiotic scenarios might be less common or more complex than the biological explanation, but they were still physically and chemically possible. To climb the cold scale, each of these alternative, non-living explanations would need to be systematically disproven. This is where the limitations of doing science via a remote robot, even one as sophisticated as Perseverance, become clear. The rover's instruments are magnificent, but they are a limited toolkit. They can map elements and certain molecules, but they cannot perform the kind of definitive analysis that would be required to climb the ladder of certainty. For example, they cannot measure the isotopic ratios of the carbon in the organic molecules. On Earth, life shows a distinct preference for the lighter isotope of carbon, carbon-12, over the heavier carbon-13. A strong enrichment of carbon-12 in the Cheyava organics would be a powerful biosignature, but Perseverance has no instrument capable of making that measurement. Similarly, the rover's cameras are powerful, but they cannot resolve a microscopic fossil, if one were even present, proving that the poppy seeds were not just mineral concretions, but were, in fact, the fossilized remnants of microbial colonies, would require slicing the rock into transparently thin sections and examining them with a powerful electron microscope, a procedure that is routine in a terrestrial geology lab, but impossible on the surface of Mars. The scientists on the Perseverance team understood this reality from the very beginning. The rover's ultimate purpose was not to make the final discovery, but to make the right selection. Its mission was to be the greatest sample picker in the history of the solar system, to identify the handful of rocks on Mars that had the highest probability of containing preserved signs of life, and to prepare them for the long journey home. The discovery at Cheyava Falls was, in this sense, the perfect fulfillment of the rover's core mission. It was a rock so compelling, so pregnant with astrobiological possibility, that it immediately became the highest priority candidate for sample return. The commands were sent. Perseverance's rotary drill, a complex mechanism on the end of its arm, whirred to life. It carefully cored a sample from the heart of the Cheyava Falls rock, extracting a pristine, finger-sized cylinder of the material, a precious cargo containing the reddish matrix, the white veins, and, most importantly, the dark, iron and phosphate-rich leopard spots. This core was photographed, documented, and then sealed inside one of the titanium sample tubes. It was a time capsule, a message in a bottle, not from another civilization, but from the deep, geological past of another world. This single tube, now lying on the Martian surface, represents the culmination of the entire cold process as it can be performed on Mars. To climb any higher up that ladder of certainty, this piece of Mars would have to be brought to Earth. That single tube, now lying on the Martian surface, represents the culmination of the entire co-elded process as it can be performed on Mars. To climb any higher up that ladder of certainty, this piece of Mars would have to be brought to Earth, the final and most audacious leg in an interplanetary relay race that has been the dream of planetary scientists for more than 50 years. The mission to achieve this, known as Mars Sample Return, or MSR, is not a single spacecraft, but a complex, multi-act drama involving at least 3 separate launches from Earth and the first ever rocket launch from the surface of another planet. It is a mission of such profound technical and logistical complexity that it makes the landing of Perseverance seem like a simple prelude. The plan, as it has been developed in a joint effort between NASA and the European Space Agency, or ESA, is a marvel of celestial mechanics and robotic choreography. The first actor, Perseverance, has already played its part, carefully selecting and caching a diverse portfolio of more than 20 rock and soil samples, with the core from Cheyava Falls being the crown jewel of the collection. These tubes now lie in a carefully chosen, flat and hazard-free area of Jezero Crater, a depot nicknamed Three Forks, their precise locations mapped to the centimeter. The next act is set to begin with the launch of the Sample Retrieval Lander, or SRL, a large stationary platform that would be the heaviest single piece of hardware ever sent to the Martian surface. After its own harrowing descent, this lander would deploy a pair of small, solar-powered helicopters, similar in design to the highly successful Ingenuity helicopter that accompanied Perseverance. These helicopters would then perform a series of sorties, flying out to the Three Forks depot, using a small robotic arm to pick up the sample tubes one by one, and flying them back to the lander. This use of helicopters is a recent innovation in the plan, replacing a previous concept that involved sending another rover, a testament to the confidence gained from Ingenuity's pioneering flights. Once the samples are returned to the lander, a large robotic arm provided by ESA would meticulously transfer them, one by one, into a small, basketball-sized container at the top of a rocket. This rocket, the Mars Ascent Vehicle, or NMAV, would be a technological first, a 2-stage, solid-fueled rocket designed to launch from the surface of Mars. When all the precious samples are aboard and the container is sealed, the MAV will fire its engines. It will blast off from the surface of Jezero Crater, punching through the thin Martian atmosphere and accelerating to orbital velocity. Its goal is to place the sample container into a stable, low Mars orbit, leaving it there to circle the red planet like a tiny, man-made moon. This is where the third and final actor in the drama enters the stage. An Earth return orbiter, also launched from Earth years earlier and provided by ESA, would already be circling Mars. Its mission is to rendezvous with and capture the orbiting sample container. This is a task of astonishing precision, requiring the orbiter to match the trajectory of an object the size of a basketball in the vastness of space, hundreds of millions of kilometers from Earth, and to safely capture it without causing any damage. Once the capture is confirmed, the orbiter would use a robotic arm to transfer the sample container into a heavily shielded and robust Earth entry vehicle. A multi-layered capsule designed to protect the samples from contamination on the outside and to protect Earth from the samples on the inside, a crucial part of the mission's strict planetary protection protocols. With its precious cargo secured, the Earth return orbiter would fire its own powerful engines and begin the long, multi-year journey back home. Its final task would be to aim itself precisely at Earth, and just before its own fiery demise in the atmosphere, release the Earth entry vehicle on a ballistic trajectory aimed at a specific, predetermined landing zone. This capsule would plummet through the atmosphere, protected by a heat shield, and deploy a parachute for a soft landing in the remote, sterile desert of the Utah Test and Training Range, a secure military facility. A specialized recovery team would retrieve the capsule and transport it to a dedicated sample receiving facility, a state-of-the-art laboratory built to the highest standards of biological containment, where the sample tubes would be opened for the first time in a controlled and pristine environment. This entire decade-long sequence of events is a mission on the absolute bleeding edge of our technological capability. It pushes the boundaries of robotics, autonomous, navigation, propulsion, and orbital mechanics. And, as of the time of this telling, it is a mission facing significant headwinds. The sheer complexity of the plan has led to escalating costs and schedule delays. In 2024, an independent review board raised serious concerns that the mission, as currently designed, was unrealistically complex and expensive, with a projected cost that had ballooned to over $11 billion. This has forced NASA to go back to the drawing board, to look for ways to simplify the architecture, to reduce the number of spacecraft, and to lower the overall cost and risk, all while preserving the core scientific objective of getting the samples home. The future of the Mars sample return mission is currently a subject of intense debate within NASA, the White House, and the United States Congress. The scientific community is united and passionate in its advocacy for the mission, arguing that it is a generational priority, a mission that will provide decades of groundbreaking science and is the only conceivable way to definitively answer the profound question of life on Mars. But the immense cost and the technical challenges have made it a difficult sell in a constrained budget environment. The fate of the Cheyava Falls sample and the answer it holds now hangs in this delicate balance of scientific ambition, technological readiness, and political will. For now, the tube lies silent in the red dust of Jezero crater. It is a vessel of immense potential, a time capsule that could contain the story of a second Genesis, a discovery that would forever alter humanity's understanding of its place in the universe. But for that story to be read, for that potential to be realized, it must first complete the longest and most difficult leg of its journey, the long voyage home. And so that long voyage home, if we choose to undertake it, will represent more than a marvel of engineering. It will be the culmination of a human quest that has transformed in both scale and substance, a journey of intellect and imagination that began in the late 19th century with Percival Lowell's earnest yet mistaken belief in a dying civilization building planet-spanning canals. It is a vision that was seemingly shattered by the stark, cratered landscapes revealed by Mariner 4, then rekindled by the enigmatic and still debated chemical signals detected by the Viking landers in the 1970s. From that ambiguity, we learned to ask a more patient and fundamental question, to abandon the direct search for Martians in favor of a geological mantra: follow the water. That strategy guided us with orbiters that mapped the planet's chemical and topographical history, and it led the rover Opportunity to the undeniable proof of ancient seas on the plains of Meridiani. This strategy, in turn, led us to the ancient lakebed of Jezero crater, with the astrobiologist rover Perseverance, and finally to a single arrowhead-shaped rock named Chayava Falls. Within that one rock, we have found the most coherent recipe for life ever discovered beyond our own world. A plausible energy source in its iron-rich spots, the essential nutrient of phosphate, and the raw material of organic molecules, all found together in a place once saturated with water. The evidence, however, remains circumstantial. A compelling but unproven blueprint for a biology that may or may not have existed. The final answer, the ground truth, now lies sealed within a titanium tube, a message from a world 4 billion years old. The quest to retrieve it is a testament to how far our questions have evolved, from the search for intelligent engineers to the hunt for a subtle chemical stain. We are now closer than ever to knowing if life ever stirred on the red sands of our neighboring world, a discovery that would forever change our perspective on our own precious, lonely existence in the vast, silent cosmos.